Okay, now we're moving on to Chapter 19, Electric Potential and Electric Field. So we're going to cover Chapters 19.1 to 19.4. So we're going to discuss the electric potential, which is related to potential difference, how that related to a uniform electric field, what kind of potential is generated by a point charge, and then also the equipotential lines that are generated by a point particle. So we've talked about the electric field, and we've talked about when you put a charge, it generates an electric field, and when you put another charge in an electric field, it can experience a force. This is similar to if you have a ball, and let's say you've got an earth, and you put the ball in the gravitational field, it's going to feel a force, and it's going to accelerate down towards the earth, okay? We know what the force is, mg, and that equals ma, so we get our acceleration 9.8 meters per second squared. We also, if you remember, if this ball is dropped from a height h, we have a certain amount of energy mgh, and when it hits the bottom, it has a certain amount of energy 1/2 mv squared. So we converted our potential energy into kinetic energy. Okay, so we're going to do a similar thing here with electrostatics. Okay, so if you look down at this picture here, we've got positive charges and negative charges. So parallel to what I just drew, minus, 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 instead of have a gravitational field, let's say you put a positively charged droplet here next to this positively charged plate. What's going to happen is it's going to be driven away. It's going to feel a force pushing away from the positive charges, but it's also going to feel a force towards the negative charge, and this thing will accelerate whoop, just like an object falling towards the earth. And it's going to have the same thing. It's going to have an initial amount of potential energy here, and right before it hits the electrons over here, it's going to be converted over to kinetic energy. So we're going to talk about the energy stored in the field here, and that's what this potential difference stuff is all about. So 19.1, the electric potential energy, the potential difference. So the change in potential energy is equal to the change in kinetic energy. Same thing with gravity, and so that's what this is trying to draw the analog to, and saying the work done on a particle to move it in this distance or through this distance is equal to the change in potential energy, just like from the first section of physics with mechanics. Okay, so read through all this, make sure you get that. But we can define this thing called potential energy, V, or sorry, not potential energy, electric potential. And it's related to this whole work thing, because work is force times distance, and it's a component of the force along the distance. So this cosine theta gives you that component along the distance. So if you drag something this way, then it's that drag force plus the distance you dragged it would be the work done. But if your force is off at some angle, you're going to take the cosine theta to the component of the force that's actually along the distance that you moved. Same thing with a charged particle. The work is force times distance. The direction of the force can be complex. You got multiple charges, things going on. So what we do is we say, well, we know the force is the charge in a field times the electric field. So the work then must be proportional to that charge. And we define a quantity, again, that's independent of any sort of test charge that you might put in there, and that's the electric potential. And so that would be the potential for the electric field to do work. And you can set it up by taking the potential energy divided by some unit charge. Okay, so that's what electric potential is defined to be. And let me see if we go down. Yeah, okay, so the potential difference then, if you have 2 points, let's say 5 volts up here and 3 volts down here, the difference between them is just 5 volts minus 3 volts. So that would be 2 volts of difference, potential difference between them. Okay, and you can just set that equal to the potential energy, change of potential energy divided by Q. So if you take your 2 volts multiplied by Q, then you can get the change of potential energy. Then you could therefore solve that, set that equal to, if it gets to the other side, if you convert all of that potential energy to kinetic energy, you can set that equal to 1/2 mv squared. And if you're accelerating an electron, you can put the mass of the electron in, solve for the velocity of the electron before it hits. but we don't have to worry about that right now because we're just getting used to the units here. So potential difference between 2 points, VB minus VA, is defined to be the change in potential energy of a charge Q if it's moved from A to B divided by the charge itself. So the units of potential difference are joules per coulomb, J over C, joules per coulomb, and it's given the name volt by this guy, Volta. Okay, so the Mars Volta is a very good band. But anyway, so the familiar term voltage is the common name for potential difference. Keep in mind that whenever a voltage is quoted, it is understood to be the potential difference between 2 points, okay? So, for example, every battery has 2 terminals, and its voltage is the potential difference between them. More fundamentally, the point you choose to be 0 volts is arbitrary. This is analogous to the fact that gravitational potential energy has an arbitrary 0. So what are they talking about here? What that means is just like if you remember a long time ago when you have a ball and you're going to drop the ball from here and you want to drop the ball down to there, and let's say this distance is height h, you could say, well, I'm starting mgh and I'm going to go 1/2 mv squared so I can solve for v, and just say v is going to be 2gh square root of that, and then that would be my velocity at this point. But what if they only gave you this total h? Well, okay, you don't really care what you're measuring from. You can say mg big H, right, minus, and then if you knew this as this height down here as h2, for example, big H minus h2 is going to be then your potential energy difference here to here. So wherever you define gravity to start, wherever h is 0, it's totally up to you. Same thing when you're dealing with circuits and volts and whatever. Usually you reference everything to ground, and so there's a 0 to 10 volts going on. But if you have a circuit where you've got a ground, but then and so we draw a ground like this, and you could have, you know, some circuit where this is 5 volts and this is, you know, 2 volts or something, and you've got ground over here, and these two are 3 volts apart, but here to ground might be 2 volts, and so on. So we'll get this figured out in a little while, but the whole point is that the potential difference between 2 points is relative to each other, and so that's all you care about. If this point and this point are 2 volts apart, you don't care if this is 20 and 18 or 5 and 7 or whatever. You just care about the difference between them, because that's what's doing the work, and the acceleration is the difference between the two. Okay, so then you've got this equation here, relates the voltage to the potential energy, and you can say that your potential energy then is charge times the change in voltage. Okay, here's an important point. Voltage is not the same as energy. Voltage is the energy per unit charge. So a motorcycle battery and a car battery can both have the same voltage, right, 12 volts, yet one stores more energy than the others, since the potential energy is equal to Q times delta V. So if you've got more charge, then you can have more potential energy. So let's do this example here. Suppose you got a 12-volt motorcycle battery and a 12-volt car battery. The motorcycle battery can move out 5,000 coulombs of charge, but the car battery can move 60,000 coulombs of charge. Okay, so how much energy then can each one deliver? So we go back to this equation here. The potential energy is charge times change in voltage. So this should be pretty straightforward. Energy is equal to Q times delta V. Okay, delta P. Oops, I drew this upside down. Delta PE is equal to Q delta V. So you've got 5,000 coulombs for the motorcycle battery times 12 volts, gives you 6 times 10 to the 4 joules. Okay. For a car battery, you got 60,000 coulombs. You multiply that by 12 volts, you got 7 times 10 to the 5th joule. So the car battery, even though it's also 12 volts, is going to have more energy in it in order to push that vehicle around or start the engine. Okay. And then there's this discussion here. Make sure you read those. So here's an example of a 12-volt car battery. It's going to a headlight. Now this can get a little confusing here. You've got a negative charge leaving the minus terminal and a negative charge entering the positive positive terminal. Okay, so the positive terminal, the negative charges are flowing into the positive terminal and leaving the negative terminals. Okay, so just keep that in mind. So when we're doing these pluses and minuses and adding these things up, that's just one thing to keep in mind. The electrons always flow towards the positive end of the battery. So let's say you've got a battery which we can draw like this, and then we can say that's the plus side and the minus side, and we draw a loop around. Well, we're going to have the charge would be flowing this way and heading towards the positive side of the battery. Not super important, but just a rule that we have. Okay, so here's a question. How many electrons then move through the headlight each second? So if we got a 12-volt battery, it runs, let's say they're putting a 30-watt headlight on there. How many electrons pass through it each section? So in order to find the number of electrons, we must first find the charge that moved in, let's say, 1 second. The charge moved is related to the voltage and the energy equation. So a 30-watt lamp. So 30 watts, a watt is a joule per second. So that's 30 joules per second of energy. So now you can see, okay, I've got joules per second, and I know that I can relate energy to that. And the battery then must use 30 joules every second. And since the electrons are going from the negative to positive terminal, we see that the change in voltage is plus 12 volts. Well, yep, because our battery's going from one side of the power supply to the other, so it's going to go towards the 12-volt battery. So to find the charge Q moved, we solve the equation here. And so the total charge we move is just the change in energy divided by the change in voltage. So we can enter these two values in, and we're moving 30 joules every second through a 12-volt battery. And so you can get that we're moving 2.5 coulombs of charge every second. So the number of electrons then, if you know that 1 electron is equal to 1.602 times 10 to the minus 19 coulombs, then you can divide that out to get your coulombs per, this is coulombs per electron, right? Then you get 1.56 times 10 to the 19 electrons flowing through that circuit, okay? So that's a very large number, right? And this is why we don't observe individual electrons in ordinary systems. There's just so many of them moving around, okay? So the electron volt then is another unit. You can take a brief pause here if you can handle this. All right, so the electron volt is you're moving from take an electron and you're going to move through 1 volt. Okay, you're going to move through 1 potential volt. Okay, that's what an electron volt is. Down here on the microscopic scale, it is more convenient to define an energy unit called the electron volt, which is the energy given to a charge like the electron accumulated or accelerated through a potential difference of 1 volt. So 1 electron volt is defined to be the energy gained by accelerating electron through 1 volt. And it's 1.6 times 10 to the minus 19 joules. Okay, so that's just a nice way to define that thing. So an electron volt is another unit, and it's a unit of energy. Okay, so just keep that in your back pocket. There's a definition here. There's this connection to energy units here. You can kind of read through that. Conservation of energy, so this is the important thing, mechanical energy. Kinetic plus potential is constant. No difference here with electrons flying around in potential fields and stuff. So for example here, calculate the final speed of a free electron accelerated from rest through a potential difference of 100 volts. Assume the numerical value is accelerated to 3 significant figures. So we want to calculate to 3 significant figures, which is three total numbers. All right, so calculate the final speed of a free electron accelerated from rest through a potential volt of 100 volts. So we've got 0 volts, 100 volts, okay? And we've got an electron, and we're going to accelerate it through this 100 volts. And we want to know how fast is it going before it gets to the end. Well, we know that we've got 100 volts of potential energy, and so we've got to convert that to kinetic energy. So we're going to say that our total initial, well, we've got it written here, total initial energy is equal to total final energy. But of course, our total initial kinetic energy is 0, so that goes away, and our total final potential energy should be 0. We're going to do a pure conversion of potential energy to kinetic energy. So the potential energy is QV. The kinetic energy is 1/2 mv squared. We just set them equal to each other and solve for V to get how fast we're going. So if you plug all that in, then you get the speed to be 6 million meters per second. So that's you can accelerate an electron to a pretty good speed with just a 100-volt power supply. Okay, so blah, blah, blah. So this is, again, it's noting about the signs. So make sure you pay attention to that because those can get confusing. All right, 19.2, the electric potential in a uniform electric field. So you've got another example here of a parallel plate capacitor, plus and minus. Your charge, Q, is going to be accelerated through this electric field. Okay, so the work done is just Q times the potential difference between them, the voltage difference. The electric field inside this charged plate is defined as this V divided by the separation distance. This works out because the electric field ends up being uniform in here, so there's no 1 over r squared, it's just over d, over the separation here. So no matter where you are, you get a nice constant uniform magnetic field. So that's a nice feature of these things. So let's keep going. Yeah, just read through this. This is just helping you understand the work done in the fields here. Yep. This is just the same equation written twice. V is ED, or E equals V over D. And that's just the electric field in between two plates. Just turns out to be a nice constant value. So they're just sort of deriving that here. All right, example 19.4. This is a pretty cool example because if you've ever seen this on the internet where sometimes they show a video of these two power poles just shorting out between each other and suddenly creating lightning between two poles in space. This is because the energy, the voltage between the two is high enough to break down air and turn air into a circuit, and this is how lightning works. So it says that dry air will support a maximum electric field strength of about 3 million volts per meter. So if you go above 3 million volts per meter, you could send electrons through. It will conduct, basically. Air will become a conductor. Okay, so above that value, the field creates enough ionization in the air to make the air a conductor. That's what I said. This allows a discharge or spark that reduces the field. Okay, so then what is the maximum voltage then between two parallel conducting plates separated by 2.5 centimeters? So we're going to go to our equations up here, and we're going to say, well, the potential between two plates, whatever it is equal to E times D, the separation. So the maximum voltage then, we know that it can only support a field strength, E, of 3 times 10 to the 6th volts per meter times 0.025 meters. Multiply those two together, and you get that the maximum voltage between you get ionization of the air and a breakdown, when the gap is only 2.5 centimeters, is 75 kilovolts, or 75,000 volts, which is a lot, okay? So, you know, it's hard for that to happen as like an accident, but, you know, people have done it. So, continuing on here, erasing. Let's see if there's anything here. Yeah, this limits the voltage that can exist between conductors on a transmission line, right? So there's a maximum amount of energy you can store in a substation between, you know, before delivering the power to the city, for example, and that limits how much, you know, you can't just make a giant power plant in the middle of one place and transmit all the power everywhere. Excuse me, because you have to limit this stuff. Okay, example 19.5. Electron gun has parallel plates separated by 4 centimeters and gives electrons 25 kiloelectron volts of energy. What is the electric field strength between the plates? What force would this field exert on a piece of plastic with 0.5 microcoulombs charge that gets between the plates? Okay, so we've got, come on, there we go, parallel plates separated by 4 centimeters, right? And this plate is going to accelerate electrons. It's going to provide 25 keV of energy. What is the electric field strength between the plates? Okay, so this is the potential energy between the plates, right? So if we go to A, we can solve for the electric field strength by just saying, okay, the voltage potential between them divided by the D is right here, 25 keV divided by 0.04 meters, and that gives you a 6.25 times 10 to the 5 volts per meter. Okay, so that's how you do that. And then part B says, what force would this exert on a piece of plastic if with a 0.5 microcoulomb charge if it got in between the plates? How much? So let's say you put a 0.5 microcoulomb charged piece of plastic in between the two. You know, plastic's everywhere these days, right? So it gets into your particle accelerator. What would the force be? Well, that's easy. That's just Q times E. We calculate what the electric field strength is between the two plates. It's nice and uniform, V over D, and solve for that, and it would be 0.3 newtons. Okay, not too bad. Note the units are newtons since 1 volt per meter is 1 newton per coulomb. Okay, so this is just something to know. The force on the charge is the same no matter where the charge is located between the plates. That's what makes the parallel plate so cool. It's nice and uniform. Okay, so remember, parallel. If you have just a point charge, the electric field changes 1 over r squared. It decreases as you move away from the charge. But if you line your charges up into 2 parallel plates, now the electric fields are nice and uniform, and it doesn't decrease with distance. You have a nice constant magnetic or electric field. Okay, so blah blah blah. So the general relationship between voltage and electric field is V over delta S, where delta S is the distance over which the potential takes place. Okay, so this is just your general rule. All right, 19.3, electric potential due to a point charge. So instead of having the parallel plates and having a nice uniform electric field in between them, now we've got a point charge. And now we want to know what's the potential due to that. So the way it works is you just say V is KQ over R. That's it. Okay, and this is because you know what the electric field is, and here's our, my pen's not working. Okay, so the electric potential of a point charge is this, and you have K is your 9 times 10 to the 9 Newton meter squared per coulomb squared, or 8.99, depending on when it's written, and then that's just by definition. So if you have a point charge and you want to know what's the voltage from, what's the voltage from, uh-oh, how do I go back? There we go. Okay, so what's the potential from here to some point out there? Well, if you know what the charge of the point charge is and you're this far away, that distance r away from it, then you can calculate what the voltage difference between this point and that point is. Okay, and then that can be used for other stuff. So your electric field, the electric field strength is F over Q, which is KQ over R squared. Now you want the electric potential, you just get rid of one of the R's, or you multiply by an R, and then you get your electric potential voltage. So this is very similar to the force being mg and the potential being mgh. It's the same idea. Your mg is your force, your potential energy is your mgh. In this case, our electric force is kq over, well, we'll call it E. Our electric field is kq over r squared. Our voltage then is kq over r. So what if you multiply this by r, it cancels one of the r's out, and then you have this. So it's the same idea as multiplying mg by distance, force times distance. It's the same idea here, force times distance. So you're taking your force at the center of this charge times the distance, and you can calculate what your potential is. So example 19.6, what voltage is produced by a small charge on a metal sphere? So charges in static electricity are in the nanocoulomb or a microcoulomb. So what's the voltage 5 centimeters away from the center of a 1 centimeter diameter metal sphere that has a -3 Newton coulomb static charge? So let's say you've got a charge here, and it's got -3 nanocoulombs of charge. It's 1 centimeter diameter, and we're going to be 5 centimeters away from it, 5 centimeters away from it. Okay, so if you remember from a couple videos ago, if you've got a uniform charged sphere, you can treat the charge as being on the surface. So the separation then is going to be 4 centimeters away, but we can also treat it, this side and that side are going to cancel out. So from the center out to here, we're going to stick with our 5 centimeter distance. So our voltage is going to be KQ over R, and that's going to be K times our charge, which is 2 or 3 nanocoulombs minus 3 nanocoulombs divided by 5 centimeters, and then that whole thing, not squared, just that. Okay, so and yeah, so there's a solution here. Our voltage potential at this point out here is going to be 8.99 times 10 to the 9 Newton meter squared per coulomb squared times our minus 3 times 10 to the minus 9 coulombs. That's a nanocoulomb divided by 5 times 10 to the minus 2 meters. And that gives you a voltage of minus 539 volts. Okay, so that would be the potential difference between out here and in the center there of that object. Okay. Yeah, I don't know if I have to do this one. Yeah, okay, well, let's go ahead and do it. So a Van de Graaff generator, it's got a 25 centimeter metal sphere. So this sphere at the top is 25 centimeters in diameter, and it produces a voltage of 100 kilovolts near its surface. So 100 kilovolts, 100,000 volts. What excess charge resides on the sphere? And so what we're going to do is just our very basic, our voltage is 100,000 volts. We've got a 25 centimeter diameter ball. So we're going to say KQ over 25 centimeters. And we want the Q. So Q is going to be 25 centimeters times V over K. And you plug all that in, and there it is. Q is RV over K. And you can get that the total charge residing on the sphere, since we have a 100 kilovolt the separation there, excess charge, then we can get that excess charge of 1.39 microcoulombs. Okay, so small charge, like it says here, small charge, large voltage. Okay. Okay, last part, 19.4. Thank you for staying with me. 19.4, equipotential lines. So we can represent equipotentials voltages pictorially, just as we drew pictures to illustrate electric fields. Of course, the two are related, right? So what we're doing here, we're taking a point charge. Let's say we have a positive charge. Now remember, we can draw these field lines emanating perpendicular 90 degrees from the surface away, and that represents the electric field. And anywhere along that line, 1 over r squared, the electric field is getting weaker and weaker and weaker, but we can calculate whatever it is along that line. Now it turns out, since this is a point charge, and if you're at a distance r away, no matter where you are, as long as you are r away, this is equipotential, equal potential. The potential from the center of this charge out to that distance r, no matter where you go, no matter where you start and where you finish, as long as you move r away, you have the same potential. This is like a mountain and walking around at the same elevation. You don't go up or down, you just move horizontally. So this is a lot easier than walking up the hill or, falling down the hill. You just walk around in a circle. You don't go up or down in the gravitational field. Same thing here. If you go around in a circle, you don't get closer or further away from the charge. You don't gain or lose any energy. Okay, so, and if you go twice as far away, right? So we can start to draw, just like in this picture, you've got your field lines emanating, and then you've got your equipotential lines connecting them perpendicular when they cross the lines. Okay, so that's the main thing. Let's see. We should have we don't have a rule book here. There's some rules here about these lines, and you can see them on display here. So let's say you've got your positive and your negative charge here. and you know that the positive charge is the source and the negative charge is the sink. So you can see all of the field lines doing that. Okay, and the equipotential lines, notice where the equipotentials are. They get deformed too. And if, let's say this is a field line, the equipotential line, boop, has to be 90 degrees when it crosses the line. So the field lines have to be perpendicular or 90 degrees when they leave the charge, but then these equipotential lines have to be 90 degrees when they cross the field lines. So those are a couple rules to keep in mind. So you can see if you trace out some of these lines, like let's say down in this figure A and B, you've got the minus signs. You can see, oh, here's a region where the equipotential lines are shared by the two charges, and this is because since they're both negatively charged, you're going to have similar electric potential lines. You can think of these as two plateaus, and they're going to have the same, and you get down to this region, they're going to have about the same potential across that point. Whereas this one you can think of more as a mountain and a giant hole. So they're always going to have different potential that are going to be isolated from each other. They don't cross over. Okay, so that's the difference between these two figures here. And then in a parallel plate capacitor where you have a nice uniform field in the center, anyway, you can see you start to lose it when you get towards the edge. But in the center, you've got nice straight, so there you go, nice straight potential lines. And notice that you're going from 100 volts, let's say, to 0 volts. You go down to 75, 20, 50. So yeah, sorry, I was getting a magnifying glass there. 75, 50, 25, and so on, right? Okay, and so those are just useful schematics for drawing and determining where an electron is going to go. These are just like topographical maps for if you're trying to plan out a hike, you're going to want to take the least steep route, and so well, maybe not an electron will want to find the quickest way down. So if you're on a sled and you jump down a topographical map, that'd be like what an electron would do as it slid around through these things. Okay, anyway, talk to you later.